Welcome back my dear students, a very good morning, good afternoon, good evening to all of you, all the participants and all the students for the TQM 2 lecture series, and this is the 27th lecture under the NPTEL MOOC series, which means that the total number of lectures, as you know, is total 40 in number. So, we are just a little bit more than the half. So, if you remember that we were discussing the factor designs and how 2 to the power k is being the different combinations you can take depending on the effects of the factors can be taken to consider different type of examples for that. So, we will continue on those same lines. So, when you are designing, so thus design C minimizes the number of words in defining the relations or relationship between the variables. And if you remember, we would try to basically take the collective effect of the factors in order to basically have the maximum effect, and obviously the error would be minimized, what is the assumptions for the errors, what type of distribution you will take. So, all these things we have been repeating in the last 27 lectures, obviously, or 26 lectures, I am sorry for that. And if you remember, we did discuss about the distributions in the first 7 lectures. So, obviously, add on to that discussion for the first 7 lectures and then the later part. So, you will understand the repetitions are taking care of the concepts which are important. So, to continue, so thus C minimizes the number of words in defining the relation that are of minimum length. Minimum length means you are trying to basically minimize some distance function. So, we call such a design a minimum aberration design. So, minimizing aberrations in a design of resolution R depending on the level of accuracy you want, robustness you want, sensitivity is also a factor. It will ensure that the design has the minimum number of main effects allied with interaction of the older R minus 1 effects. So, which means that minimum number of 2 factor interaction allies with the interaction of order R minus 2, then R minus 3, R minus 4 would happen, which will give you the overall picture what is the effect. The following table, which we will consider in the next slide, presents a selection of the k 2 to the power k minus p. Now, these are the factorial designs. So, the concept of k and p have already been discussed in the factorial design models, though briefly. I do understand that we did not go into the depth. So, we will again repeat that accordingly. So, for presents a selection of 2 to the power k minus p fractional factorial designs for k less than or equal to 15 factors up to about 128 runs depending on n. So, if you remember, each factors had samples. So, we considered initially the number of observations, or I would not use the samples means the number of observations makes a sample. So, number of observations in each factors was considered equal. So, if you had say for example, k factors and each of them had n number of observations, the total set of observations was k into n, and it could be different also. So, we could take the averages, so on and so forth, which we did discuss in the 24th, 25th, 26th lecture. So, the suggested generators in this table will result in the design of the highest possible resolution depending on the accuracy we want. So, there are also the minimum aberration design which can be considered. So, this sorry for the slide is a little bit too intense in the sense there are lot of information here, and considering that I am only trying to give that in one slide, it may not be immediately possible for you to read it. Plus, please bear with me because everything has been taken from Montgomery's book. So, that if you can either check it in the library or find it in your college, no need to buy, which I keep saying that. If you can get those informations, it will be very helpful to refer what I am saying with respect to the slides which are there. So, the number of factors which is k are given on the first leftmost column. So, we start with 3, 4, 5, 6, 7, 8, 9, then you go to the next table which is 10, 11. So, the other combinations increases. So, the fractions would be there would be, if you remember, it was 2 to the power k minus p. So, obviously, we would have 2 to the power 3 minus 1, then you will have basically 2 to the power 4 minus 1, 2 to the power 5 minus 1, 2 to the power 5 minus 2, 2 to the power 6 minus 1, 2 to the power 6 minus 2. It will continue, and for the 11, when the number of factors are k is equal to 11. So, some of the combinations are 2 to the power 11, 11 is the factors minus p, it can be considered as 5, as 6 and 7, so on and so forth. So, the number of runs which you do depending on the combinations, the design generators can be a combination of AB, can be a combination ABC, can be a combination ABCD, depending on what you think is the highest influence, and the number of runs would be dictated according to the experiment and the number of observations which you have for each factors. Based on that, we have this table which gives you, again I will repeat, the first column number of factors, then the fractions which is technically 2 to the power k minus p, then any of the number of runs, and the design generators which will basically give you the best possible effect of the factors from which you can find out what are the minimum number of the optimum number of factors based on which you can predict the maximum amount of dependence. That is what you are trying to do, and obviously there would be errors, but as I mentioned that the white noise of the errors would have certain properties, certain distributions, certain mean values, certain variances which we did discuss. I will discuss that time and again. So, consider this example. Obviously, we have considered the aluminum example, the smelting example, different type of examples, then the battery one where you want to design the battery at different temperature using different materials. So, we will continue consider another example also. To illustrate this use of the table which you have just considered, suppose that we have 7 factors where the k is given, and then they are interested in estimating the 7 main effects, their individual effects, and obviously we will try to replace them in the combined one, and getting some insight regarding the 2 factor interaction. So, we are willing to assume that the 3 factor and higher interactions are negligible. So, obviously 3 factors, 4 factors, okay. If you remember, I did mention in 2 or 3 classes the factor design could have been basically like 2 to the power k, 3 to the power k, 4 to the power k, but we are limiting it to the 2 factor model in order to basically 2 things: minimize the number of calculations, minimize the overall complications in the calculation, but still get the best effect based on which we can predict the effects of the factors. So, this why, and obviously 3 and 4 would give us very theoretically very nice results, but practically their essence would basically be lost, because if you are able to do with the 2 factor model. So, we would stick to that in order to minimize our complications, but still get the best answer. So, we are willing to assume the 3 factor model. So, I am just repeating it. We are willing to assume the 3 factor and the higher interaction which are basically negligible. This information suggests that a resolution of 4 design would be appropriate, based on which we will basically find out the effects. So, this table which you have just discussed shows that there are 2 resolutions of the 4 fractions. So, one is basically 2 to the power 7 minus 2, another is which basically would result in 32 runs, and 2 to the power 7 minus 3 which will result in 16 runs. So, the appendix will contain the complete alias relationship for these 2 designs. The aliases for 2 to the power 7 minus 3, which is basically 16 runs, are given in the next table, which is 10 1. Notice that we will notice that all the 7 main effects, which is the 7 2 to the power 7 minus 2, which is, or 7 minus that 7 or the value of k. So, this notice that all the 7 main effects are realized with the 3 factor interaction. So, k minus p is 3. Therefore, the design will satisfy our objectives, that is, it will allow the estimation on the main effects, the secondary effects, tertiary effects, and obviously as you combine them, the combined effect may decrease, but we will keep it maximum to a certain level. Level means the combination such that we get the maximum effect or the maximum relationship which is coming out. Therefore, this design will satisfy our objectives, that is, it will allow the estimation of the main effects and it will give some insight regarding two factor interaction, which is our main focus. Again I am saying it is 2 to the power that whatever k minus p is, not 3, not 4. It is not necessary to run the 2 to the power 7 minus 2 design, which is k minus p, which would require about 32 runs. So, the appendix 10 J shows that this design would allow the estimation of all 7 main effects which is there, and that the 15 of the 21 runs for the two factor interaction could also be uniquely estimated, and you can find out the results. So, this is probably more information. So, this is probably more information about interactions that is necessary would be obtained, but we will keep it to the minimum level because calculations is also an effect. So, we will notice that it was this table was constructed considering the 2 to the power 4 design, which is basically A, B, C, D, which you have. So, the combinations which you will have would be basically combination of A, B, C, combination of B, C, D, combination of A, C, D, which you are mentioning as E, F, G. So, the generators which you will have once you find out would be A, B, C, E, then another generator will be B, C, D, F, another generator would be A, C, D, G, which you will see in the table. The complete and we have already checked in that table which is just finished in the last slide. The complete defining relationship, which is basically for I, which is the indicators and the overall factor design which you are considering are A, B, C, E. So, combining them to find out the best effect. Another is B, C, D, F, one is A, D, E, F, one is A, C, D, G, one is B, D, E, G. So, these are the factors. So, the factors would be named differently, like it can be temperature, it can be pressure, it can be humidity, depending on the example which you have. To continue, let me continue reading it. It will be B, D, E, G, C, E, F, G and A, B, F, G depending on the level. So, obviously, if you take the 3 factor model or the 4 factor model where k changes, obviously, the complications will come where the different combinations of the indicator so called variable or the combinations of the factors would increase. So, and obviously, increase would result in complications not in the answer, but in the calculations. So, you have to consider them accordingly. So, once you have the 2 to the power 7 minus 3 where k is 7 and p is 3, the fractional factorial designs are. So, if you consider the runs starting from 1 to 16. So, the basic designs which you have considered was the factors was A, B, C, D, and the combinations if you consider are given. So, when you combine them, so you have basically E, which is combination of A. I am reading the last 3 columns first and then come to the different combinations you are taking. You will basically have E, which is a combination of A, B, C, F, which is combination of B, C, D, which you have found out, and the last one is G, which is a combination of A, C, D. Now, if you consider the different factors or the levels of interactions which is taking place between these individual factors, which is A, B, C, D, and obviously, the k becomes 7 because you are considering the 5th one as E, 6th one as F and 7th one as G. So, if I combine all of them, so the combinations are, say for example, I am arbitrarily taking one, the first row which is the first run. So, here the effects we are considering they are on the lower side, that is why it is minus. Then if we consider the second row which is run 2, there I am considering the effects of A and E as positive and G as also as positive, and we consider the effect of B, C, D and F as negative. Now, if you pay attention to this second row which is the second run, I have repeated that again and I am going to basically say that here if A and effect is positive, so obviously it would mean D does not have, C does not have and D does not have. But let us consider concentrate of E. So, what is E? E is a combination of A, B, C. So, obviously, the effect of A is there. So, it will be positive. Now, let us concentrate on the second last factor which is the 6th factor which we consider as F. So, what does F combined have? It is B, C, D. So, does it have A? Your answer is no. So, hence the effect is on the lower side which is negative. Let us go to the last factor which is the 7th one which is G, which is a combination of A, C, D. Does it have the effect of A? Yes. So, it is positive. So, if you do this in these combinations, so consider the say for example, the 14th run. So, 14th round has A as positive, B as negative, C and D as positive. So, if you consider the combinations which is happening and depending on the positive and negative effect, you will find out that A, E, F and G would basically have an effect on a positive side or the negative side, that means higher effect, lower effect, and similarly the 16th round. Now, remember one thing, the positive and negative which you are taking out are the effects on the higher side or the lower side. So, obviously, they can be 3 stages of effects also, like high, medium, low, or it can be 5 also. So, I am giving hypothetical examples, it can be 5 also, like very high, high, moderate, low, very low. So, these combinations obviously would result in a complicated table. We are not going to consider that, we are just mentioning that positive and negative effect as a plus effect, which is going to increase its influence, negative means is going to decrease its influence. Consider that on those lines. So, now blocking the fractional factorials, we will consider it further. So, occasionally a fractional factorial design requires so many runs that all of them cannot be made under homogeneous conditions, where the conditions of the say for example, you are taking the factors as temperature, humidity, pressure. So, if they are homogeneous, the effects of them we are going to consider on the same level, that may not be possible. In these situations, fractional factorials may be compounded in blocks to find out their combined effects. So, consider the fractional factorial design with the defining relationship where I, the indicator factors of the combined, where you have A, B, C, D, C, E. So, you are combining the factors individually, you have A, you individually you have B, you individually have C, individually you have E. So, you combine them to find out their combined effect. Similarly, other one is B, C, D, F, again we combine them individually, you have B, C, D, F. So, you take their effects in a collective manner. So, obviously, the positive and negative would be counted accordingly, and the last being A, D, E, F, you will do the same thing. So, this fractional design contains 16 treatment combinations, as we have already seen, and we can find it out. So, suppose we wish to run the design in 2 blocks of 8 treatment combinations. So, 16 combinations would be broken into 8 and 8. It can be other combinations also, but we are taking 8 and 8. In selecting an interaction to confound with blocks, we note from examining the Alice structure as given that there are 2 Alice sets involving only 3 factor interactions. So, even though the combinations are A, B, C, D, but in that case we find out that dividing 16 runs into 2 blocks of 8 8 each, you have 3 Alices which where the factor interactions are only 3 in number. So, the table suggests selecting A, B, D to be confounded with the blocks such that we can find out the combined effect accordingly. So, now we take the factorial factor design as 2 to the power 6 minus 2. So, if it is 6 minus 2, the design generators are, we are considering E as A B C and F as B C D. So, defining relationship, the indicator which you get are, as I mentioned, A B C E, B C D F and A D E F, based on that we proceed. So, aliases when we find out, and the combinations would be A would be clubbed with B C E and D E F, that means the effect factors are being combined together in order to reduce the overall complication of calculations. Similarly, you will have B, you have and in that case it will be A C is equal to B E. So, these equality means the effects we are going to combine them in that manner. The third one is C, which is A B E and B D F. Similarly, the fourth one is D, which is equal to B C F and A E F. Considering that, we basically continue. So, once we have the blocks are defined accordingly. So, the blocks are in block 1 you have, I will read it, the combined effects are for the factors, considering that you have initially started with A, B, C, D, and obviously later on you combine those factors under the headings or give the name as E in different combinations of A, B, C, D, then F different combinations of A, B, C, D, G different combinations of A, B, C, D. So, once the blocks are there, the first block would basically have, I am reading some or I repeating some of the factors, which is A B F, C E F, A B C E, so on and so forth till B C D F, and from block 2 you will basically have AE, ACF, so on and so forth till the last one, which is the combination of A, B, C, D, E, F. So, this gives you the combinations of 2 to the power 6 minus 2 factors, where K is 6, again I am repeating, why 6, because you have basically considered them at one level lower, and P is basically that P value is basically 2. Now, we will consider the allied structures or the factorial designs for the regression model. So, let us first consider the polynomial regression or the simple regression concept and then explain accordingly. So, the method used the polynomial or the regression model representation of the model, which is y. So, these bolds means they are vectors or matrices. So, you have basically L, say for example, k number of independent variables, which are basically denoted by capital X1, capital X2, capital X3 till capital Xk. So, these are the factors which affect independent variables, and obviously, the combination of these independent variables, considering the multiple linear regression to be true, you consider the overall effect is there such that you are able to predict, forecast, whatever word you use, the dependent variable, which is y. So, obviously, when you are trying to predict, there would be errors. So, if you plot the errors along with the best fit line. So, in regression, what you do want to do is you want to basically fit the best fit line. So, the best fit line would definitely not go through all the points, because if you join all the points, they are not a best fit straight line. So, there would be differences between, or consider the distance would be there between the actual coordinates and considered in this, let us consider. So, even though I did mention that you have basically k number of variables which are independent, but consider that you have to make our life simple, and I can only explain that in the 2 dimensional and the 3 dimensional case. Consider that you are without drawing. So, if you read, if you understand what I am saying, it will definitely make sense, and obviously I will explicitly mention that later on. Consider you have the very simple concept of y is equal to mx plus c, which you have all done in basic class 9 or 10. Now, what you have is y is basically the value which you want to predict, x is basically the readings which you have taken, and there is only one x, and one x means it is a scalar, obviously x would have different values, and m is the slope. So, that means slope, the rate of change of y which is taking place of x, and c is the intercept. So, if you have in a 2 dimension, what you have in the x axis all the x values which are plotted, in the y axis you have the y values plotted, and if you basically fit a best fit line. So, where it intercepts the y axis, that is the height is c, and the tan of this angle of y by x, whatever y and whatever x length you take, the tan of that angle, that is equal to m. Now, if you go to a 2 dimension one, so you will basically consider that x1 is being measured from I am consider that where I am standing is the origin, it is going towards you, I am measuring x1, and if I consider, say for example, x2 being measured from my point, again it is basically the origin, it is going to the right, and I am measuring the y values along the vertical direction. So, if you again plot the x1 and x1 and x2 as coordinates, you will basically be able to predict y. So, they would be a 3 dimensional points, and in the 3 dimensional case they would be a plane. So, obviously, if you go to the higher dimension, there we use the word a hyperplane. So, I am not going to go into such details or such complications. So, when you consider the regression model, what you have is basically some x's, these are the actual values which you observe, you can find out the reading, consider you want to predict, say for example, the rainfall, and you think the pressure, temperature and humidity at certain place are important to predict the rainfall. So, hence pressure, temperature, humidity are x1, x2, x3 correspondingly, and the rainfall is y. Now, when you get the actual values of the humidity, pressure and temperature, and you predict it, obviously they would not be exact values. So, there would be a difference, which is the error. So, if you check this slide, it basically gives you an error, that error term which is the white noise in the regression concept, that would have some properties. So, the technically the properties which we generally consider in the regression model are, I will mention one by one, and I am only mentioning them. I am not going to go into the actual theoretical either proofs or the mathematical equation as of now. I will come to that later on. So, basically what you have, the distribution of each of the x's are considered to be normal. Hence, the y distribution is also normal, and also the fact that the error term which you have will also be normally distributed with the mean value of 0 and a standard deviation which is fixed, which is sigma square, or at the best it is 1. We can basically consider that the variance of the errors as 1 depending on the problem formulation. Point 1. Point number 2, these values of beta 1 to beta k which you are taking for each individual independent variable. So, for the case of temperature, humidity and pressure, we consider there are 3 values which is k is equal to 3. So, these values of beta 1, beta 2, beta 3 which we have are technically the rate of change of y with respect to x 1, x 2, x 3, considering the other 2 are fixed, which means that if beta 1 is the rate of change of y with respect to x 1, we are considering the x 2 and x 3 are fixed. So, if we are considering the beta 2 as the rate of change of y with respect to x 2, then we are considering x 1 and x 3 fixed. So, it is basically the so called marginal rate changes of the dependent variable with respect to the independent variable. We also consider the relationship or the covariance or the correlation existing between all the combinations of x 1, x 2, x 3 is non-existent, which is 0. We will also consider the covariance existing between the error and these x's, x 1 to x k are 0. So, there are different very simple mathematical notation which I said I am skipping, but just I am telling on a very for the general understanding. So, once you listen to this, you will understand how the regression model is done. So, if you come back to what I said for the last 3-4 minutes, you come back to the first bullet point, it mentions that y, which is the dependent variable, is equal to x 1. Now, x 1 is basically here is a matrix, because y values you are taking from y 1 to y n. What is n? You will ask that question. N is the number of readings which you have. So, obviously, if you have y 1, y 2, y 3, y 4 till with the y n values. So, correspondingly you will have x 1 values, it readings are from x 1 1 to x 1 n, where the second suffix would basically mean the number of readings, which is the first period reading, second period reading, third period reading till the nth period reading. See, similarly, you will have x suffix 2 1 to x suffix 2 k 2 n, then similarly you will have for the kth one x suffix k 1 till x suffix k n, and the errors would obviously for each term they would be for each reading the set of readings. So, x 1 1, x 2 1, x 3 1 till x k 1. You have y 1 and you have an error term also. Similarly, in the second row, if you are imagining, it will be y 2, then the x values would be x 1 2, x 2 2, x 3 2 till x k 2, and similarly you will go to the k the nth one. So, if you consider the x values, it is a matrix of size n cross k. The errors are the size of n cross 1. Beta is the size of k cross 1, because there are k number of betas, and y value is basically n cross 1. So, if you consider that, so y is the n cross 1 vector of responses, which I am again repeating. X 1 is the size of n cross p 1 matrix. So, here I am considering p as the number of reading the x's which you have. What I have been mentioning was k, continuing the design matrix expanded to the form, and beta is basically of size p cross 1, which I mentioned k cross 1, vectors of the model parameters, and epsilon is the errors, which is also n cross 1. Obviously, I mentioned the errors. So, the least square estimators is given by beta hat. So, obviously, hat means the estimator is given by the inverse of the multiplication of the transpose of x factor into the x matrix into its x multiplied by the transpose of x into y. So, with this again I will come to the effect of why, how we are trying to find out the beta. Again I will repeat it in the very simple qualitative sense, not in the quantitative sense. So, with this I will end the 27th lecture and continue more discussion about these factor models in the concept of regression later on. Have a nice day. Thank you very much.